My name is Steve Bedell. I work at the IBM T.J. Watson Research Center in Yorktown Heights, New York. I work on all sorts of electronic materials, mainly in an attempt to make high-performance CMOS even more high-performance. We work on everything from silicon to compound semiconductors, really at the materials level, at the very beginning stage of circuit manufacturing. Having worked on rigid semiconductors for a number of years, recently we had more of a breakthrough invention where we could take some of the classically high-performance materials, silicon, gallium arsenide, things like that, and we could make them flexible. So the history of flexible electronics has always been taking new materials that are flexible and trying to make good circuits out of them. And this is kind of the flip side of that, where we take materials that are known high performance, we can actually build the high performance circuits natively on those wafers and then make them flexible afterwards. The secret sauce is some knowledge of fracture mechanics. So basically it's a fracture-based system, and it's one of these things that I guess there's always a certain amount of luck that goes along with that. You know, it's a mode of fracture referred to as spalling. It's pretty obscure. The field is pretty obscure and small, and what it is, it's always been a failure mode. So it's been a problem, right? So this is an example where we took lemons and made lemonade out of it. So it's an interesting story where this material failure mode that has been known for decades, and people have always sought to avoid. All studies, all papers prior to this have always been how to not do it, right? So it's one of these things where we said, hey, maybe we can do this in a controllable manner at a wafer scale and be able to literally fracture very thin layers off the surface of any brittle substrate. And with some engineering, it turns out it's very simple to do it, but figuring out what to do and what not to do is really what we spent the last few years figuring out, and getting it from a kind of a parlor trick into a science, into a system of actually layer transferring materials. The question is, how thin of a layer can we peel off? That's really the people get excited. When I tell them we can do thick layers, not many people are very excited, because but when you can peel off very, very thin layers by fracture, it's remarkable. So we've demonstrated that we can peel off as thin as 200 angstroms, which is 20 nanometers, which is really thin. It's so the atomic, the lattice constant of silicon is 5 angstroms. So it's 20 of those lattice constants that you can peel right off a surface of a material. So yeah, we can peel off very, very thin layers, and for those who are interested, we can peel off layers that are up to, say, maybe 80 microns thick, which for the photovoltaic people, the solar people, they actually want thicker materials for better conversion efficiency. We've recently shown that we can do more exotic and expensive materials, like gallium nitride is a very promising material that's used in every white LED you see. All the high efficiency LEDs are made out of that, and it's a very expensive material to make, very complicated material to make, and they've recently been able to make whole wafers out of gallium nitride at a premium cost. So the idea of being able to peel off very thin layers of those things and reuse that substrate over and over dramatically changed the cost structure. So solid state lighting or power electronics is very compelling to use this technology. Obviously photovoltaics, and our recent demonstration of peeling off finished circuits, really it's in the imagination limited stage what we can do with that, to take conventional high performance circuitry and be able to render it flexible or thin. Some of the limitations are we're using a stressed metal layer that's deposited on the surface of the wafer to actually induce fracture and peel it off. So if it's a material that's not sticky, that you can't stick to, you don't have good adhesion, that can be a problem. If you have a bunch of layers, if you've built a circuit that has many, many layers in there and one of them happens to be weak or poorly adhered, fracture likes to go there and delaminate the structure rather than spall it or fracture it off. So there are some limitations. We have been able to take, luckily most metallurgy and most contact metals for circuits and for a variety of technologies are well adhered to their substrate, and that's been borne out by experiment. We've been able to take substrates that have had processing levels done on them and peel everything off, the contact metals, the whole device and everything, and that's been useful. But there are limitations in that regard. Serendipity is always a part of science as long as you're allowed to do it, and luckily at IBM Research we can do that. So there's always a directed element to our research, very well-defined programs, but along the way One day you come in and you find some crazy thing that you never thought you were going to find, and there's a lot of latitude for that. And this is an example of that. Actually, I was working on solar. I was given the mandate to try to come up what is the cheapest way to make a solar material. And so the idea was like take a big chunk of the ingot. Instead of cutting it with a saw, you can peel it off. So we were working on ways to peel off layers. So it had some directionality to it, but it was an aside to I was already working on a different program, so I just started working on this kind of after hours on my own, and a couple months later we had it.